Osazone formation. This is the structure of phenylhydrazine. Actually, when I was in class 12, I couldn't understand that why always this nitrogen shows the basic properties or the nucleophilic properties. Why not this one? That's why I have just shared the answer here. This one nitrogen is giving its lone pair to the ring. Actually, this nitrogen has two lone pair. This nitrogen has two lone electrons, okay? And these are actually, this nitrogen is giving this lone pair here inside the ring, and a resonance structure you can get. Again, you can say that this will come here, this will go there, or this will come here, like this. So this lone pair of the nitrogen is involved inside this ring. That's why this nitrogen cannot show the basic property or the nucleophilic activities. This nitrogen is free, there is no conjugation, and it has one lone pair. So this lone pair can show the basic properties. This is your aldose. You are reacting it with phenylhydrazine and you are getting phenylhydrazine derivative, which is osazone, phenylosazone. Osazones are generally yellow crystalline solid. Formation of it results in a loss of chirality center at C2, but does not affect other chirality centers. That's why D-glucose, D-mannose yield the same phenylosazone. This is the structure of the phenylosazone in case of D-glucose and D-mannose. As both these two are losing their chirality, that means not two, actually this one is losing its chiral property. That's why the D-mannose and D-glucose both gives same phenylosazone. Although D-fructose is not an epimer of D-glucose or D-mannose, D-fructose also gives the same osazone, and these three gives the same phenylosazone. And now come to the mechanism. Oh, this is a larger one. Okay, see this. This is your aldose and this is your phenylhydrazine. At first the basic nitrogen is attacking here and this bond is being opened. Now what is happening? This nitrogen is losing one proton and forming this. After that again the lone pair of nitrogen attacks here and this OH2 plus leaves. So ultimately you will get this structure, phenylhydrazone with one condensation, okay. Then actually a rearrangement occurs, which is said amatory rearrangement. This is the amatory rearrangement, and after that you will get an imine structure. This another molecule of phenylhydrazine reacts with this imine, and here this nitrogen will attack here, and in the same kind it will form C double bond N NHPH. And then the third number of molecule of phenylhydrazine, this one is the third molecule which is involved in the same reaction. This will attack in this carbon and this will here go here. Then after that this proton will be lost, so we will get this, and at last this will go out as ammonia and you will get the final osazone structure. So look at this mechanism very carefully. Osazones of aldohexoses is stabilized by intramolecular hydrogen bonding. Now look at here in case of this portion. Actually this OH is attacking here and forming a ring-like structure, and this double bond is taking a proton, so this is becoming NH, and this NH is forming a hydrogen bonding with this nitrogen, with the nitrogen which is attached with the phenyl ring. That means this nitrogen and this proton which is attaching with this nitrogen, they are making a hydrogen bond. So you will get a intramolecular hydrogen bonding. Because of this, the phenyl osazones are stabilized. Now in case of ketose, the same kind of reaction occurs. You just see it yourself. I am not describing this. Just try to understand. Now this mechanism is supported by the observation that when osazone prepared by the reaction of glucose with N15-labeled phenylhydrazine is treated with ordinary phenylhydrazine, unlabelled osazone is obtained accompanied by the expulsion of labelled ammonia. So this one is your carbonyl compound and you are giving a labelled phenylhydrazine. So at first this will form the phenylhydrazone, and then after the rearrangement the PH NH2 group will leave and you will get this kind of imine structure. Then again another molecule of phenylhydrazine, unlabelled phenylhydrazine, will attack here, this one, and form this one, and another molecule of phenylhydrazine will attack at this carbon, and this NH group will be just expulsed, becoming NH3. So by doing this labeling, by doing this method, scientists have seen that this NH3 bears the labeled nitrogen. That's why they proposed this kind of mechanism. Amadori rearrangement. The Amadori rearrangement was discovered by the organic chemist Mario Amadori. In 1925, he reported this reaction while studying the Maillard reaction. The Maillard reaction he was studying, and then he just invented this rearrangement. The reaction is important in carbohydrate chemistry, specifically the glycation of hemoglobin. The rearrangement is usually preceded by formation of the alpha hydroxyimine by condensation of an amine with an aldose sugar. The rearrangement itself entails intramolecular redox reaction, converting this alpha hydroxylamine to an alpha ketoamine. Now what is ozone? Removal of the phenylhydrazine groups in osazones by hydrolysing these with hydrochloric acid or by treating these with benzaldehyde in the presence of acid yields dicarbonyl compound. These dicarbonyl compounds are known as osones. So you have this osazone, and if you treat with HCl or just benzaldehyde in acidic medium, you will get a dicarbonyl compound. These dicarbonyl compounds are called ozones. Osones. Don't say it ozone, okay? Ozone is the O3 is the ozone, and this is the ozone. How to convert an aldose to a 2-ketose by the osazone formation. By this you can just convert an aldose to a 2-ketose. That means you can just convert the glucose to fructose by this manner. So at first make the phenylhydrazone, that means osazone. At first form the osazone, then treat it with benzaldehyde in the acidic medium. So these phenylhydrazine groups will be removed, and you will get the dicarbonyl compound, which is ozone, which is ozone, and just treat it with zinc and acetic acid. So if you treat it with zinc and acetic acid, this will just reduce this aldehyde group, not this carbonyl group. And after reducing this aldehyde group, you will get 2-ketones. By this procedure, glucose can be converted into fructose.